For this video, we will be solving performance task 3, and again, as I mentioned in our announcement, certain typos were found in the creation of the code to solve for our solution, so this will be the final and correct method, hopefully. Okay, so let's start. So first problem, we only have two problems here, and as mentioned, both problems will be 15 points each. So for the first one, we have the house from up. So considering a large helium-filled party balloon, so helium is used widely compared to hydrogen because helium is less flammable compared to hydrogen, so it's a safety issue. Though hydrogen is able to displace more weight because of it has lesser density, but again, as a safety precaution, helium is a better choice compared to hydrogen. So the lifting force on the balloon due to the outside air is the net resultant of the pressure distribution exerted on the exterior surface of the balloon. Okay, so using this fact, we can derive Archimedes' principle, namely that the upward force on the balloon is equal to the weight of the air displaced by the balloon. So what does it mean by that? So imagine this balloon right here. So this balloon of a given volume has an internal pressure with a gas inside it. So the gas here is helium, okay, where the gas outside is air, so not the hands. So I'll be using my stylus. So again, this is air and this right here is helium. Okay, so what happens? So your ambient pressure, okay, at sea level will be exerting pressure, so it has air molecules here, will be exerting pressure on the balloon. So if we have a balloon, so let's imagine a balloon formed into a cylinder, so a cylindrical balloon. So why are we making a cylindrical balloon? So that we can have the forces at the side as equal. So here we can see that the forces now that we have are the following. Okay, now theoretically, because we have an atmosphere and our atmosphere is directly affected by gravity, and because of hydrostatic equation, okay, the tendency of gases is to move from high pressure to low pressure. So natural tendency is for it to move up towards the low pressure area. So that's why if you let go of a balloon, it will start floating up because it has greater pressure here compared, okay, so anything with low density, so it will start floating. Okay, same as when you have an aquarium. Okay, you drop a coin and styrofoam, so styrofoam will start lifting up because it has a lower density compared to your water, compared to a coin. Now going back to the balloon, so this will exert pressure here, so pressure, so the pressure outside is 101,325 Pascal. So this is the amount of pressure exerted at all sides, and we also have pressure right here. Okay, now how about inside? So inside the balloon, your helium will also be exerting pressure on all sides and all corners of the balloon. How much? The same pressure. So same pressure external is equal to the pressure internally. So because it is made out of gas, all the gas particles will start to fill up the whole balloon, and it will exert the same pressure from the outside. So if it has lesser air, crumple up siya gamay. If it has more air, it will start expanding until mabuto siya if masobrahan. Okay, so again, the amount of pressure will be the same. How about the temperature? So the temperature, ambient niya, temperature of air outside is 288.15 Kelvin, because it's at sea level, or that's roughly 15 degrees Celsius. Okay, so how much will the temperature be? So it's safe to say it's also equal, because if there will be exchange of temperature, there will be dispersion of temperature, so we can also assume that temperatures now will be equal. What will be different? So what's going to be different are the densities of the two, density of air and density of helium. So going back to our problem, the upward force. So where does the upward force come from? So the upward force comes from the amount of weight dispersed by your object. What does it mean by that? So going back to the example we gave a while ago. So for example, I have here a box of water, or let's say an aquarium na ko'y bula. So let's say I have a ball standing on top. So na siya gamay nga i-disperse. Okay? So in this illustration right here, because the amount of water that I dispersed is little, so the force also is little. Okay? Mao na siya, if you put the ball, you put your hand here on top. So let's say na imong hand there, you put a little bit of force, so the amount of resistance imo ma-feel will not be as much. But the moment you submerge it all the way to half, so you will be using more force. Okay? So the more air or the more fluid is being displaced, the more force is being used. So asa man ang force imong gistorya dia? So the resistance coming from the fluid, that is the lifting force ato mahatag. So how does that relate to our example? So let's say we have here air. So air ni siya dere. We have helium. So the bigger my volume is, the more air I disperse and the more lift put. But that's just not volume lang, okay? So it is not the volume that dictates, but again the weight. And how do we solve for the weight of the balloon? So very simple. First, we know the density. Next, by multiplying the volume, so that's kilogram per cubic meter multiplied by volume, that's cubic meter. So you have kilogram, and since it's weight, you have to multiply it by gravity. So that's meter per second squared. You have Newton. Okay, so for English units, that's log, cubic feet, feet per second squared. So the amount of weight being dispersed. So what disperses it? Okay, so it's the weight of air, ato butang weight of air minus the weight of the helium inside the balloon. So when you subtract the two, that's the amount of weight dispersed. Okay, so how do we use all of this that we talked about sa atong example? So consider a large helium-filled party balloon with a volume of 2.88, lifting force, okay, so 0.002377, and the weight of the house is 124,700. So assume that the molecular weight of air is 28.80 grams per mole, and that of helium is 4 grams per mole. So how do we do this? Okay, very simple. So first, so we know that ito ang iyahang lift is the weight of the displaced air. The displaced air, that's weight of the air displaced by one balloon minus the weight of air, the weight of helium inside a balloon. Okay, so muna siyang weight displaced. So that means that if we have, so kanina this is per balloon. And since the house weighs 124,700, simply multiply it by the amount of weight that each balloon can carry. So that's weight air minus weight helium. Okay? And how do we solve for the weight of helium? So that's equal to density of air, that's 0.002377 times volume. The given volume is 2.88, so that's log per cubic feet times 2.88 cubic feet times taas yun eh. So this is density, volume, and gravity. So gravity, to have the exact value, that's just 9.80665 over, that's meter per second squared, over 0.3048. This is meter per foot, so you'll get feet out of here. Okay, so this is for the weight of air. Minus, so first, how do we solve for the density of helium? So density of helium. So based on the equation of state, we know that P is equal to RT. Okay, so pressure helium, temperature helium. Now we know that equal ni siya, equal. What we don't know is R. R, as mentioned by our notes, that's gas constant divided by its molecular mass. Save niyo yung symbol. Gas constant, Ru, over molecular mass. So we can therefore say, since equal man siya, okay, this is P air, T air, R air. So because these two are equal, therefore we can have a ratio between, so density of air, we can have a ratio of the density of air directly to density of helium. So what is the ratio? So density of air, so ratio, tupad sila. So density of air with, since if you look at this, they are inversely proportional, so ato say multiply density of air, R air, is equal to density of helium, R helium. Okay, molar mass of helium, I mean. Molar mass of helium. Molar air, molar helium. So that gives us density helium is equal to, wait, this is wrong there, sorry. So since R is under, M is under, so dapat di ay R is under. Okay, so this should be density air, R air, is density helium over R, M helium. This is M. So density helium is equal to density air times over then molar mass air, molar mass helium. So we simply put that here, that's 0.002377 4 over 20, yan to, 4.0028.80, 28.80. How about the units? So they cancel out ra, pwede na nato dili na so we don't need to convert. So times volume and gravity. So I won't write it down now. So let's put it in our calculator. 124,700, that's 0.002377 times 2.88. Sakto ba? 2.88. Yep. 2.88 times 9.80665 divided by 0.3048 minus, so I'll just copy everything here and multiply it by 4 divided by 28.8. Okay, so therefore our answer is 650,000 balloons are needed to carry our house. Okay. So usually balloons nga ibaligya sa daan are almost a foot in diameter. So iyahang radius is 0.5 as roughly let's say mga 1 kapin, 1 cubic feet. So you'll be needing a million balloons to carry a house this size. But in our example, since we have very big balloons, so this is a good answer. Okay, next. So next one is a flow over a flat plate perpendicular to the flow. So this example, ako ma-think dyan is a motorcycle barrier used by our dear officials or proposed by our dear officials. So there are many problems to this. One very quick example is kanisiya, this right here. So if this were kanisiya gisulob man, but usually a main problem if you have barriers that are attached this way, one of the main problem is mahimo siyang moment arm matumba. Okay, so the next problem is if so kanisiya, so moment arm force is being applied right here on your surface. So kanisiya, this will begin to turn. Ang nagkupot in taon ani dere kanisiya. So kanisiya, kusog-kusog ang dagan, na chance this will turn, malabay jud ni siya. So ang force nga gigamit to pull, ang force put on by the air, so kana lang daan. And then after that, so because moment arm ni siya, kani moment arm nagpull sa ni siya, na possibility ma-upturn ang imong bike. That's just one. What else? We can also talk about kani when they wear. Okay, so if tigmotor mo kay bawo mo nga there is a lot of force exerted on the handlebar. So if imo nang bitaron, there's a chance if you pull on it too hard, muwili na ng bike, especially if you accelerate too hard. So that provides a stability problem. Another problem is, so aerodynamically, the bikes are, especially sports bikes, so they've been studied to produce as less drag as possible. Even if dili na siya sports bike, if you wear your helmet, dako kay difference when you wear a full-faced helmet and a motard nga helmet, na nanay difference sa head lang na siya. How about your body? So bigger guys will experience more drag compared to smaller guys because of wider surface. So mo na siya, if you drive, if you crouch like this, you will experience less drag compared if you stand up in ane. So what are the effects? So number one is stability. Okay, the more forces you add to an already two-wheeled bike, and butangan ni magdaghan kay external forces, so it provides stability problems. And wala pa na ilabot ang inefficiency of it being able to stop particulates from, so if you look at it here, okay, so naadyo na siya downwash. Ang downwash creates a backflow, a back pressure. So wala kayo gamit no. So what's the best way to combat that? The best way is already what they're wearing, a full face mask. So a full face mask already provides the necessary aerodynamic answer to the problem of needing a barrier. So kaning full face helmet already solves that problem. Okay, so going back to our problem, consider a stationary thin flat plate with area of 2.12 meter cube. So this is a very big plate. So then for each face oriented perpendicular to a flow. So imagine this is a 2.12 meter cube. That's not meter cube, square meter. And then for each oriented, the pressure exerted the front face of the plate facing the flow is 1.36. So this right here, 1.36 atm, and it's constant over space. Pressure exerted on the back of the plate facing away from the flow is 2067, and it's constant over the face. Calculate the aerodynamic force in kilonewtons. So we know based on our past learnings, we know that wait, teamwork ako. Okay, so stylus, please work. Okay, working siya. So we know that pressure is equal to force over area. Therefore, if we are looking for force, that's just pressure over area. So in our case, what's needed is the aerodynamic force in kilonewtons on the plate. So it's the resultant force, so Fr. So again, there are two forces here. There are two pressures. You have the pressure up front, so if this is your plate, and the pressure on the back. So how do you find the resultant force? So that's just force at the front minus force at the rear. So that's pressure at the front over times the area minus pressure on the rear times the area. So since we are solving for it in kilonewtons, we simply divide this by 1,000. So 1,000 newton is equal to 1 kilonewton. So let's put that in our calculations. So here 2.112. Okay, 1.36 first. 1.36 times 11325 times the surface of 2.12 minus, so that's 2067 point, so times, so the conversion from pound force per square foot to kilopascal is 0.047. So this is 47.88026. So that's 47.88026. So this is in pascals pa. So times the surface 2.12. So this will give us pascal units divided by 1000. So this is pascal times meter squared. That will give you newton. So here pascal times meter squared, your newton. So our answer is 82 kilonewtons. So that's a lot of force. So let's try to check if our answer is correct. Okay, correct and correct. So finally, this ends our video, and I hope you learned something for today, and apologies for the error. That's it.